This is the final video of Module 6. We're going to discuss how to use a theory-based approach when we have quantitative data, and then we're going to do example 6 to go through an example of that. So if you're doing a hypothesis test related to mu and you have a sample mean x bar, then we know you could use a simulation in order to help you create a distribution of sample statistics. It turns out if you meet certain validity conditions, you could use a theoretical mathematical approach to that instead. So as it reads here, when you have a sample of quantitative data that is roughly normally distributed, so it's a mound-shaped like a bell curve, or if your sample size is 20 or more, that meets the validity conditions and you'll be allowed to use a theoretical t-distribution to model that distribution of sample statistics. So when you do have that t-distribution, the center of it is going to be mu, the population parameter, just like it was when we used a simulation-based approach. And the standard error, that is the standard deviation of the null distribution, is found using sigma divided by square root of n. Recall that sigma is the standard deviation of the entire population. However, it's very, very, very rare that we would actually have a standard deviation for the entire population. So instead, we do often find ourselves estimating that standard error using S divided by square root of n. Remember, S is the standard deviation from your sample. So again, we can use this theory-based approach when we meet the validity conditions. And if we do meet those validity conditions, you're going to find that our theory-based approach has the same sorts of conclusions that we would have gotten from the simulation-based approach. So let's go ahead and try example 6. Example 6 reads as follows. A cookie company claims that their cookies have a mean of 24 chips per cookie, with a standard deviation of 3.1 chips. So notice the cookie company is claiming that about all their cookies, so about the entire population of cookies. I randomly sample 40 cookies. I find my sample had a mean of 19.6 chips per cookie with a standard deviation of 3.8 chips. So I want to know, does it seem like the claim that the company is making seems true about all their cookies? So this, I haven't really said that, do I think it's smaller? Do I think it's bigger? I'm just wondering, does it seem accurate to say that the population mean is 24? So part A asks us to write the null and alternative hypothesis. So I would write that the null hypothesis is that the population mean equals 24. The mean number of chips per cookie for all cookies is 24 chips per cookie. And the alternative hypothesis is that mu is not 24. So the mean number of chips per cookie for all cookies is not 24 chips per cookie. Part B asks us to identify a standard deviation of the null distribution for a simulated distribution that I've given below. Remember, that's called a standard error. The standard deviation of your null distribution is called a standard error. And we see it's listed right here, SD equals 0.505. So that is the standard error, the standard deviation of this null distribution that we're getting from a simulation. Part C then asks if we can explain why we can use a theory-based approach instead of only using a simulation. So we are allowed to use a theory-based approach here because we meet the validity conditions. It said that we are allowed to use a theory-based approach if our sample is roughly normally distributed or if our sample is more than 20. And since we sampled 40 cookies, we have met the validity conditions. Part D asks us to use the appropriate formula to find the standard error of the distribution of sample statistics. So when we're dealing with quantitative data, the standard error is found by taking sigma divided by square root of n. In the problem, remember, they told us that the cookie company is claiming that it's a mean in the population of 24 and that the standard deviation for the entire population is 3.1. So we're going to use sigma equals 3.1. And remember, n stands for the sample size. So square root of 40 would go in the denominator. And then finally, we're going to pop that into the calculator. Again, remember, if you don't have a good calculator, you can just use the Desmos.com website and go to scientific. All right, now here we are at the Desmos calculator. I'm going to first hit this fraction button because overall it's a fraction. Up in the numerator, we have 3.1. I click down into the denominator and hit the square root button and put a 40 underneath that square root. And then I hit enter, and it says that its standard error is 0.49 approximately. All right, so when I use the formula, I got a standard error of 0.49. Recall, when we did the simulation, the standard error was 0.505. So very, very close. They're both very close to a standard error of 0.5. All right, part E says to calculate the value of the standardized statistic, give the symbol. So remember, a standardized statistic is either a z-score or a t-score. It's telling you how many standard deviations away from the hypothesized value of the mean is your observed statistic. So since we are talking about quantitative data here, we're talking about a t-score. There's our formula for t-score. We're going to take our observed statistic, subtract the middle of the null distribution, the mean of the null, and divide by the standard deviation of the null distribution. So for our problem here, our observed statistic was our x bar, our sample mean that we actually observed from our sample. When we sampled 40 cookies, it looks like we got a mean of 19.6 chips per cookie. So our statistic is 19.6. The mean of the null distribution, recall, that was the hypothesized mean from the entire population of cookies. That was 24. And the standard deviation of the null distribution from what we calculated a moment ago is 0.49. I do want to make a quick note here. When you're dealing with quantitative data, you often are going to have several standard deviations going on in your problem. In this problem, for example, we have a population standard deviation was given to us, 3.1. We had a sample standard deviation from our sample of 40 cookies. So our sample standard deviation was 3.8. And we also have the standard deviation of the null distribution, which is about 0.5. That's also called the standard error. So you want to be careful when you're calculating a t-score that the standard deviation you're using is actually the standard error. It's the standard deviation of the null distribution that goes here in your t-score calculation. Don't accidentally plug in like sigma or s there. What goes here is the standard deviation of the null distribution. Okay, again, we need to calculate this out on the calculator. So again, you could go back to Desmos and you could type that whole thing back in. So up in the numerator, I have the 19.6 minus 24. And I click down into the denominator and I put the 0.49. And I get a t-score of about negative 8.98. That is a very, very, very low statistical value in the null distribution. That means our observed statistic is almost 9 standard deviations below the mean. That is super low. Very, very unusual. This would be a very, very unusual statistic to get if the null hypothesis were true. In other words, this t-score is telling us that we have very strong evidence against the null hypothesis. It's very strong support of the alternative hypothesis. And then finally, part F asked if we make the same conclusion with the theory-based approach as we make with the simulation-based approach. Yes, we do. If you come up here, here is the null distribution from the simulation. You see it's centered at 24, and our observed statistic of 19.6 is off the charts low. It would have a p-value of 0. There are no simulated samples like that. And when we used a theory-based approach, we got a t-score that is very, very big in absolute value. It's almost 9 in absolute value, 9 standard deviations below the mean. So yes, we have the same conclusion with the simulation approach and the theory-based approach, and that makes sense because we met the validity conditions.